Hi, I'm Chris,
And I'm Adam.
and today we're going to teach you guys a little bit about RLC circuits. So to go over our table of contents, first we're going to teach you guys some real-world applications of RLC circuits. Then we're going to go over the theory of them. Next, we're going to go over some of the tools that we can use to create an RLC circuit. And then lastly, we're going to go over some of the mistakes that we've made and teach you guys how to not experience them. RLC circuits can be used in a lot of different ways in the real world, but here we're going to talk about two specific ways as a filter and then also in electronics. As a filter, RLC circuits tend to work by only allowing a specific range of frequencies to be accepted. This means that whether it's a radio frequency you're looking for or adjusting the bass and treble for the music coming out of your speakers, or also to clean up some signals in communication. In electronics, RLC circuits can be used for charging smartphones and toothbrushes. They can be used in metal detectors and even surge protectors. With charging, the way that it works is that the RLC circuit will resonate at the same frequency as the receiver coils, which allows for efficient energy transfer. And for something like a surge protector, the RLC circuit will allow for the transient energy to dissipate before things become a problem.
So a little bit about the theory. RLC circuits are seen as analogous to like a spring mass system or any really mechanical oscillator. They're the easiest electrical oscillator to create and understand. Basically, they consist of a resistor, an inductor, and a capacitor. That's what the RLC stands for. And by changing the resistance, capacitance, and inductance, we can get three types of systems out: an underdamped system, an overdamped system, and a critically damped system. We're going to get more into what that means now. So with these three types of systems that I just talked about, we need to characterize the dampening. We do that through a dampening parameter called xi. Uh, this xi is given by the equation on the screen and is proportional to the resistance to capacitance and inversely proportional to the inductance. Um, and this it also characterizes the three types of systems, this xi term. And it's when it's less than one, it's underdamped. When it's equal to one, it's critically damped. And when it's greater than one, it's overdamped. We're going to get into what those three mean now.
For an underdamped system, as Adam said, xi has to be less than one. When it's underdamped, the system will oscillate as it decays. So, for example, you've got something like a guitar string. When you pluck a guitar string, it'll make a lot of noise quickly and then it'll slowly decay. That decay, though, as you'll see, the string will oscillate back and forth across its equilibrium position. And then it'll slowly approach just steady state at which it's no longer vibrating and the string is just at the equilibrium position. For our system and RLC circuit, it works the same way. We'll see ideally our capacitor discharge and charge up back and forth across its equilibrium position until eventually it'll decay to having zero charge in itself.
For an overdamped system, when xi is greater than one, the system takes a slow path of return to equilibrium, where it never oscillates and it slowly just falls back to equilibrium. This is in real life analogous to something like a soft closing cabinet door to prevent a slam. It's given by the equation on the screen, but generally just the characteristic of it is that it takes a while to get back to equilibrium and it doesn't oscillate.
For a critically damped system, xi has to equal one. This system means that the system will take the fastest path to equilibrium as possible. It doesn't oscillate, it's not slow, it's as fast as possible. Here, the system will dissipate all of its energy extremely fast. An example of this in real life is like car shock absorbers. When a car drives over a bump, the shock absorbers will be displaced from equilibrium and then they'll move as quickly as possible back to that equilibrium position to make a smooth ride for the drivers. You don't want it to you don't want your car to be bouncing and oscillating back and forth. And you also don't want your car to slowly reach the equilibrium position because then you're going to constantly feel the car moving up and down or moving down. So you want it to get as quickly as possible and it'll improve stability and comfort.
So a little bit about the taking the measurements while you're doing this in a lab. First, you want to calibrate your oscilloscope and your oscilloscope probes. To calibrate the oscilloscope itself, you just have to click the self-calibration button in the menus. But to calibrate the probes, it's a little bit more complicated where you have to plug the probes into the oscilloscope itself. There should be a square wave source on like the bottom right of the probe, and then plug the ground into the associated ground to that, and then mess around with the trimmer. And you should have a key that you can stick into the probe and then twist to mess with the trimmer. And on the oscilloscope itself, you'll see a square wave, and you want to make that square wave really clean, because sometimes it'll have like rounded edges, and that's noise and something that you need to. That's the calibration step. Uh, and then next you want to hook up your function generator and your oscilloscope to the circuit. If you have your components in series, like we did, you want to hook up the function generator just like any other battery, where it's hooked up to either end of the circuit. And then the oscilloscope should be hooked up to one end of the capacitor and then the ground to the other end of the capacitor. Um, that will give you the results that we were looking for.
Now we're going to move on to some of the mistakes that we made and that hope we can teach you guys not to make. For starters, we worked really hard for results, but we weren't working hard for experience and knowledge. What that means is we were just forcing things to happen without actually understanding or trying to figure out what is supposed to happen or what is actually happening. We rushed into our goals. We didn't take a break. We didn't stop and learn about the theory and learn about all of our materials and all of our tools and things like that. And we just didn't understand what was supposed to happen when we set up each of our circuits. And so that led us to just waste a lot of time and not be efficient. Uh, Another thing that we made a mistake on is when things weren't going well, we didn't take a step back and examine our entire system as a whole. We often just assumed that this was a problem or that was a problem and try to fix that little thing, but it didn't actually fix the problem because we never looked at the entire system as a whole and figure out, okay, is the problem with the function generator? Is it the oscilloscope? We didn't ask ourselves these questions and instead we just kept rushing into things.
Thank you for listening. And always remember, this parrot only squawks at resonance. It's an RLC squawkulator. What? This is the bloopers.
This is the bloopers. This parrot only squawks at residents. It's an RLC squawkulator.
Oh, I have to say that shit.
So for some real, is that how you spell application? Hold on.
You
That is some
got
real
this.
that was bad.
So to determine, I said that wrong.
Yeah, you did, didn't you?
Yeah, I did say that wrong. That was me. Fuck. Hate
No,
that. I
you're
hate that I just said that. I hate that I just
yeah,
said that.
you're calibrating the probes for sure. What is happening? Mistakes. That's great. That was class. That was clean. I like that.
Little square wave.
Sorry.
Um,
That's a wrap, folks.
that's a
That's
wrap.
that's a wrap.